Hey Chemistry, we're starting a new unit on intermolecular forces, and previously I had talked to you about the difference between a polar covalent bond and a non-polar covalent bond, and that is due to the difference in electronegativity. Now we're going to talk about polar molecules. A polar molecule is a molecule that has a different partial charge on different parts of the molecule related to where exactly those polar covalent bonds are located. So we're going to differentiate between a polar molecule and a nonpolar molecule and how then that results in these intermolecular forces. So we're going to be able to predict whether molecules are polar or nonpolar based on their geometry and the difference in electronegativity between the atoms. So polar molecules, because they have these partial positive and negative charges on different parts of the molecule, are attracted to each other the same way ions are attracted to each other in ionic bonding. So for instance, water molecules have a positive side near the hydrogens and a negative side near the oxygens. And then what can happen is that these molecules will line themselves up in a arrangement where the positive side and the negative side are attracted to each other. So these molecules start rotating in space to try to line up positive to negative, and that creates somewhat of a crystalline structure among these molecules. So this image here kind of shows how these water molecules will line up. Now, these are not full charges, so we do not use a positive and negative symbol like we do with ionic bonding, like ions. Instead, we use this symbol here, which is the lowercase Greek letter delta, and we say it's delta positive and delta negative, and that represents a partial charge. Remember that in polar covalent bonding, they are still sharing the electrons. It's just that one side, one atom, is sharing it more than the other, and therefore ends up having this somewhat of a partial charge to it. Nonetheless, because they have these partial charges, these atoms will line up positive to negative, as the hydrogens on one water will line up with the oxygen of another water molecule. So let's kind of see this in action. So here we have a bunch of water molecules that have their partial positive and partial negative charges. Let's see how they would arrange themselves. So you can see this water molecule is going to line up positive to negative. This water molecule positive to negative. Now you'll notice here when this water molecule approaches, it's lining up positive to positive. Well, that's going to result in repulsive forces. That's going to push that water molecule away. And what will end up happening is that water molecule will rotate in space so that it can line up positive to negative. And here's another one lining up negative to positive. Polar molecules, because they have these partial charges, are also attracted to ions who have full positive and negative charges. And so what will happen is if you take an ionic substance like sodium chloride, salt, and drop it into water, the water molecules come in and start lining up positive to negative. So for instance, you're going to see here that this chlorine ion has all the hydrogens facing it because they have partial positive charges. This sodium ion has all the negative oxygens facing it. And so the water molecules come in and start lining up all around the sodium and chlorine ions. And this is how salt dissolves in water. The sodium chloride is surrounded by water molecules, and the water molecules start teaming up in a group that literally can pluck the ions off of the crystal, causing the crystal to shrink smaller and smaller as the ions are sent off into solution. And that's how ionic substances like various salts dissolve in water. Now, there's another group of molecules out there called nonpolar molecules. If all of the bonds that are in the molecule are nonpolar covalent, then the entire molecule is considered to be nonpolar. And that means that there is no distinct positive or negative end to that molecule. There's no place on that molecule you can say, well, there's the positive side and there's the negative side. And so water molecules are not attracted to these because there's no place where the water molecules can line up because there's no opposite charges for them to line up to. So nonpolar molecules usually do not mix with polar molecules. They usually do not interact very much with them because they basically have no place where the water molecules will start to line up, or where other polar molecules, it doesn't have to be water, other polar molecules are simply not attracted to them. So oil is a non-polar molecule. You can see this chain of carbons with hydrogens around it, and every single bond in the molecule is non-polar. And so when you try to pour oil into water, the water is simply not attracted to it, and so they do not interact very much. And so you'll see this separation. The water molecules are more attracted to each other than they are to the oil. And so when you pour the oil into the water, the water molecules simply push the oil away as they're trying to force themselves to be next to each other. Water is more attracted to itself than it is to the oil, and so the water molecules stick together and the oil is pushed out and separates by density. Okay, so take a look at this molecule here. This is ethanol. Ethanol is C2H5OH. And I want you to think about this. Is this molecule polar or non-polar? Now the black is carbon, the white is hydrogen, and the red is oxygen. So look at that molecule, and is it a polar molecule or a non-polar molecule? Well, we're going to look and say, well, this portion of the molecule right here is all non-polar bonds. Carbon-hydrogen bonds are non-polar. And of course, carbon-carbon is nonpolar. Anytime something's bonded to the same element, it's nonpolar. So you'd say that that portion of the molecule is nonpolar. But take a look here. Carbon-oxygen is a polar bond, and the electrons are being pulled toward the oxygen. Oxygen-hydrogen is also a polar bond. The electrons are being pulled toward the oxygen. So in this case, a polar portion of this molecule is going to show up. The oxygen is going to take on a partial negative charge, and so we put delta negative. That hydrogen is going to take on a partial positive charge. So ethanol is indeed a polar molecule because there is a distinct positive end, this hydrogen, and there's a distinct negative end, this oxygen. And those are places where water molecules can then interact. This portion of the molecule we would say is non-polar, but all you need is one part of a molecule to have a distinct positive and distinct negative end for the molecule to be declared a polar molecule. Okay, in part two, we're going to look at how those interactions between polar molecules and non-polar molecules allow us to create solutions and what can mix with what.